this is part 2 of the chapter 14 review. In this video, I'm going to talk about how to use graphical data to calculate delta H and delta S of a reaction. That's this slide. And then I'm going to talk a little bit more about Le Chatelier's principle. So first, this is sort of like a slide that I showed you in chapter 14, where it shows you a version of the Van Hoff equation that is written in the form of y equals mx plus b. And so we can use this equation to graph linear data if we recognize that y is the natural log of k, and we put that on the y-axis, and if we recognize that 1 over t is x, and we put that on the x-axis. Now we know that that ln k is equal to y, and 1 over t is equal to x. And so the other values in this y equals mx plus b equation, if you were to actually graph this on Excel or something like that and get these numerical values in the equation, will tell you something about delta H and delta S. So if you graph it this way, what is m in your equation, this number here, 66,662, equals this negative delta H over r. Because, again, we're mapping this y equals mx plus b form of the equation onto this equation that we got when we graphed it in Excel, where it's actually giving you the values for m and b. So, likewise, we can say that b is equal to delta S over r. So we can use this equation to pull out those different combinations of variables and set them equal to the numbers in the equation that we get when we graph it when we graph it on Excel. So for example, if I wanted to find delta H, then I would set this m, the slope, which is negative delta H over r, equal to the actual number of the slope that I get when I graph the data. Now it becomes an equation with one unknown, because remember I know r is a constant, and the value of r that I would use is going to be this value, 8.314 joules over moles times Kelvin, because I should recognize that if I am going to be calculating a delta H, the units for that is going to be joules. And so I want something that has joules in it. That's my thinking process. And really it's going to be joules per mole. So whenever I find a delta H of reaction, I want to know what's the delta H for 1 mole of that reaction happening. So that's why the per mole is in that value of r, and it will remain in the units of delta H after I do this. So do a little bit of algebra. Multiply both sides by r, multiply or divide both sides by -1, and what you should get, I'm just going to do this really quickly on my calculator, so I'm going to take I'm going to take 66,662, and I'm going to multiply it by r, because that's how I isolate delta H on both sides. And so negative 66,662 times 8.314 is going to give me negative 554,227. And now I just take that negative off because both sides are negative, so I'm going to multiply or divide by -1. And the value that I get is 554,227. Joules per mole. And now you know why most delta H's are actually given in kilojoules per mole, because these are big numbers. So just be aware of the units there. I can do a similar thing to calculate delta S, except now I'm going to use this b term in the equation. So I'm going to say that b, delta S over r, is equal to the value I get for b in this equation, and I can set them equal to each other. I can take, again, 20.1 and multiply it by r, because I'm multiplying both sides by r to isolate delta S. Same value of r, 8.314, and that is a value of 167. And but its negative delta S equals 20.1 times R, so I have to change the sign of this in order to get delta S and not negative delta S. And so I'm going to change the sign and I get negative 167. And that is how you are going to use a y equals mx plus b equation to solve for delta H and delta S. So you're just basically using it to set up these algebraic equivalencies. So try these on your own and see if you can get the answers that I just got. Okay, finally, Le Chatelier's principle. So imagine a system at equilibrium. You've got a reaction, it's at equilibrium, you do something to it. You change one or more of the following. You change the concentrations, the pressures. Remember that changing the pressure for a gas is the same as changing the concentration. You change the temperature or the volume in some way. And Le Chatelier's principle is going to state that the system responds by reattaining equilibrium in a way that reduces the impact of the imposed change. So it's going to shift away from that change and counteract that change. And so I think of it this way. You do something to perturb the equilibrium. You add more of something. You take away something. You change the temperature. You compress the volume. You do any of those things and more. You could probably think of more examples. The reaction, the machinery of the reaction is going to respond by making more reactants into products or more products into reactants. Those are the choices that the reaction has. It has these two reactions going on at the same time, the forward and the backward reaction. It can either shift forward and make more products or backward and make more reactants to counteract the change that you just made. This occurs by making one reaction faster than the other. That's the only thing an equilibrium system can do. It can make one reaction, the forward or backwards, faster than the other one for a period of time. During that period of time, it's not at equilibrium. It's going toward equilibrium, but it's not at equilibrium because one reaction, either the forward or the backward, is faster than the other for that period of time. So say I add more nitrogen, well, for a finite period of time, the reaction in this direction is going to be faster because it wants to produce more NH3 and bump up those concentrations or pressures of NH3 so that it can reattain equilibrium. Once it's at equilibrium, then these two reactions will be equal again. The rates of those two will be equal again. So this happens over a finite time period. I think this is something that some of you were struggling with and I wasn't clear enough about. But what the basic goal of this is to reattain K. Once you add more nitrogen, for example, you're not at K anymore, you're at Q. You're not at equilibrium. And so the reaction has to shift one direction or another to make all the concentrations such that they equal K again when they're in that K expression. Once they equal K again, it's at equilibrium. Both reactions are the same rate. K will be the same as before because K is a constant, except in the case of changing temperature, because you know now that K is temperature dependent and we actually change the value for K when we change the temperature. But all of these other changes, changing the concentrations or pressures, changing the volume, changing the pressure, would not change K if we're at the same temperature. And so the machinery of the reaction is going to go into overdrive one direction or another in order to make that K equal K again. That Q equal K, again, I should say. So you don't have to be at equilibrium. You can have a reaction that has both a forward and a backward reaction not be at equilibrium. This is something that maybe some of you struggled with too. So what if you're constantly making a change? For example, what if you're constantly adding a reactant or constantly taking away a product? Well, the reaction is really never going to be at equilibrium, and that's okay. It's just that you can think about it as the reaction is just constantly trying to keep up with your changes. but you keep making changes, so it can't keep up. So this is the Haber process. It's a reaction that uses nitrogen gas from the air, combines it with hydrogen gas to make NH3, ammonia, which is a precursor to the nitrogen that you can put in fertilizers. Nitrogen is a really important element for plant growth. So we need ammonia in order to be a precursor for many of these fertilizers. So if we want to make ammonia, well, we've got to do something. We've got to perturb this reaction so that it can't just sit at equilibrium, because then we won't maximize the amount of NH3. We'll still have some N2 and H2 hanging around. So what can we do? Well, we can constantly siphon this NH3 off into another vessel, and that would take away product. And so the Le Chatelier's principle would say, well, the equilibrium will then shift. The reaction will just shift to try to reattain that equilibrium by making the forward reaction faster and producing more NH3, okay? And if you constantly take away NH3, then it's constantly going to be shifting in this direction and producing more NH3 to try to counteract that. And that's how you manipulate an equilibrium. You could also be adding more and more nitrogen and hydrogen as it goes along, and the equilibrium would constantly be responding by getting rid of that to make more NH3. So Le Chatelier's principle is important to know because it gives you tools to manipulate the equilibrium to make the thing that you want to make. And our bodies do this all the time. Very, very few, if any, of the reactions in our body are actually at equilibrium, because the cell is constantly transporting reactants or products to certain places, taking them away, making them more concentrated. And you don't want to be at equilibrium, otherwise the reactions wouldn't go forward in the direction you want them to make your cellular processes work. So Le Chatelier's principle can be used to by us humans to manipulate a reaction, but it's also used for biological systems. And I just want to emphasize that if equilibrium is reestablished, when it's established by Le Chatelier's principle, you're going to have different concentrations of these three things than you had before. That's okay. They're still, if it's at equilibrium, they're still going to equal K. So look at this example for this reaction here, right? We have started out with different concentrations, 3 different experiments. We get the same K value in the end, but look what we have in our pot. Here, we have different concentrations than we have here and here. But you can have different concentrations if it's at equilibrium. They just have to equal this K value when they're put into the K expression. So I don't want you to be thinking that when Le Chatelier's principle happens, that after the equilibrium is established, that you have the same concentrations as you had before. That is not going to be the case. However, you will have them equal K again. So once you put the concentration, in this example, of NH3 to the power of 2 over N2 times H2 times the power of 3, you're going to have new concentrations after you make this change that you're doing, or that you're perturbing the equilibrium. Once it reattains equilibrium, the concentrations will be different, but when you put them into that K expression, it will equal the same number. So I hope that helps. Please let me know if you have further questions. The more specific that you can be about these questions about Le Chatelier's principle, the better I can help you answer them. And I know that sometimes if you're really confused, you don't even know what questions you have. So my goal with this is to help you ask a more specific